Hi everyone, I'm Natalie Bills, a physical oceanographer trained in the Department of Oceanography at the University of Cape Town and currently working at Yale University as a postdoctoral associate. I'll be providing this week's critical eye from the science guy, or rather the science gal. Sorry you can't see me, my webcam's acting up. Okay, so let's start with Haley's lecture on the role played by oceanic circulation in Earth's habitability. First of all, well done Haley for putting together a comprehensive introduction to oceanic circulation. As Haley's lecture demonstrated, the ocean is not static, and like the atmosphere, the major role played by the ocean in contributing to the habitability of our planet is of the fact that it transports heat from the equatorial regions to the polar regions, making the tropics more bearable and bringing much needed heat to the high latitudes, which receive very little sunlight. So really, the number one role of the ocean in contributing to the habitability of the planet, I would say, is by helping the atmosphere in transporting heat from the equatorial regions to the polar regions and making a far larger region of the Earth pleasant to live in. Here this figure that I've put up here is showing sort of our best estimate of the amount of heat transported polewards by each ocean on average. Notice that the units are in petawatts, so that's 10 to the 15 watts. 1 petawatt can power about 1 billion light bulbs per second. So the ocean is transporting a tremendous amount of heat polewards. The black line here shows the total. This is the mean, the zonal mean over each basin. So this is the total amount of poleward heat transport. And as you can see, the ocean does a lot of its heat transport out of the tropical regions. So it peaks, at about 15 south and 15 north. And then you can see here it's decomposed into the role played by the Atlantic. And notice that it's always positive in the Atlantic, so there's a net northward transport at all latitudes in the Atlantic. Whereas in the Pacific, it's polewards in the northern hemisphere towards the North Pole, because it's positive. And negative here shows that it's polewards towards the South Pole in the southern hemisphere. So you've got the symmetric distribution in the Pacific Basin. So Haley mentioned that this oceanic circulation is forced, 1, by winds, causing Ekman drift and setting up the basin scale wind-driven gyres that she explained, and 2, by density variations in the ocean, driving the thermohaline circulation. And just an interesting note here, it's called thermohaline circulation because the density variations that drive it are primarily controlled by either temperature, so thermo, or haline, because it's salt. So that's where sort of the term thermohaline circulation comes from. Haley also mentioned that oceanic motion is forced by the gravitational pull of the moon and the sun, giving rise to tidal motion. However, when it comes to forcing the large-scale currents in the ocean that contribute to the ocean heat transport that you see in this figure, tidal motions are regarded as playing a smaller secondary role, mostly through its role in mixing the ocean when tides interact with the ocean floor. Haley also mentioned Earth's rotation as a forcing of oceanic motion, but I would argue that the Earth's rotation itself does not give rise to oceanic circulation, but rather acts on oceanic motion via the Coriolis effect, as Haley explained. Put it this way, if there were no winds or density variations to force oceanic motion, then all the Earth's rotation can do is simply cause the ocean to rotate with the Earth. This would not act to transport heat from the equator towards the poles. So in this particular diagram, it's mostly the thermohaline and the wind-driven circulations that are causing the heat transport. Haley placed a lot of emphasis on the role of the thermohaline circulation, but something that I would like to point out using this figure of the poleward heat transport is that the wind-driven upper ocean circulation plays just as an important role, if not more important role. Let's compare oceanic heat transport in the Atlantic versus the Pacific. While the Atlantic is both wind-driven and thermohaline circulation, The thermohaline-driven meridional overturning circulation causes net northward heat transport at all latitudes. So here you see this, as I mentioned earlier, the purple line, which is showing the Atlantic, is always positive. So that basically indicates that the heat transport is northward throughout all latitudes, going from 60 south all the way to 70 north. This is because of the thermohaline overturning circulation in this basin. But if we turn to the Pacific, which is the green line, what we see is that the wind-driven overturning circulation, which is quite symmetrical about the equator, gives rise to northward poleward heat transport in the northern hemisphere, which is positive, and southward poleward heat transport in the southern hemisphere. So we have this more symmetric about the equator view, and essentially this is most of this transport, this poleward transport, is due to the wind-driven overturning circulation in the gyres of the Pacific Ocean. In theory, it's easy to conceptually separate what wind-driven and what thermohaline circulation should be, but it's much harder in practice when observing currents in the ocean. Another factor is that the thermohaline circulation needs a mechanism to mix water, the water that sank to the bottom in the North Atlantic, back up to the surface. Where and how this happens is still debated by oceanographers, and the wind-driven circulation might be playing a key role in this upward branch of the thermohaline circulation, making the two types of circulation hard to disentangle. One of the key reasons for the ongoing debate is that the subsurface ocean, where our satellites can't see, is hard and expensive to measure. Haley gave some great examples in her talk of how we are trying to solve this problem. My favorite is South Africa's new ship, the SA Agulhas. As Haley mentioned, from a human-centric point of view, we also care about more than just the role of oceanic circulation and heat transport. We also care about it because it determines the habitats of life, of the life that we fish from the ocean. Another important aspect is that oceanic circulation affects sea surface temperature. And sea surface temperature is the first-order forcing of atmospheric circulation. What do I mean by first-order forcing? I mean that if you rank the importance of every factor controlling atmospheric circulation, the nature of sea surface temperature comes out as one of the most important. So if you want to forecast changes in atmospheric conditions such as temperature, wind, and rainfall, you need to have a good idea of what the sea surface temperature forcing is. To be able to do this, to be able to predict atmospheric conditions, we then need to have an understanding of the oceanic processes that affect sea surface temperature. So really, we need to have a good idea of oceanic circulation in order to predict atmospheric variability. And this a great example of illustrating this is looking at the El Niño Southern Oscillation. So towards the end of our lecture, Haley introduced us to the concept of ENSO, which is short for the El Niño Southern Oscillation. I would like to try and do a better job than the video she showed in explaining to you, one, why we actually care about ENSO, and two, the amazing way in which the ocean and atmosphere interact to give rise to El Niño and La Niña events that affect atmospheric conditions around the world. Okay, so why do we care about SST variability, sea surface temperature, SST, variability in the eastern equatorial Pacific? Why is it such a big deal? What makes this region so special? So we have to appreciate that the atmosphere is a highly nonlinear system, and so its weather is hard to predict more than 7 days in advance. There are, however, modes of variability in Earth's climate system that allow us to have some skill in predicting the statistics of weather, which we refer to as climate. For example, will the summer be hotter and drier than average, or wetter and colder than average? El Niño and La Niña events form part of a mode of variability that we refer to as ENSO, the El Niño Southern Oscillation. And of the modes of interannual variability in the climate system, climate scientists have identified that ENSO has the largest impact affecting regions across the globe. So this figure here shows you our current understanding of the teleconnections. So how variability in this region here, the eastern equatorial Pacific sea surface temperatures, actually lands up affecting the weather patterns via propagation through atmospheric waves, known as Rossby waves, lands up actually affecting the climate sort of in North America, South America, even Southern Africa, and it actually has a strong correlation with the rainfall we have, the summer rainfall we have in Southern Africa, Australia, and sort of the maritime continent, and the rainfall in sort of the monsoonal regions. So what we see is robust relationships between variability in sea surface temperatures in this region and then this sort of seasonal rainfall and temperature at regions in other regions of the globe as it's communicated through the atmosphere. So when I first heard about ENSO, I thought, what's the big deal? Why are sea surface temperatures in this region, in the Eastern Pacific, so important? And how come they're able to have such large impacts all over the globe? And I'd say this figure pretty much sums it up. When you look at this world map, you basically see that the surface area of the ocean, of the Pacific Ocean alone, is about a third of the surface area of the planet. So this is a huge body of water. It's a huge body of water that can move and have its own sort of a life of its own. And when you land up heating this area, the Eastern Equatorial Pacific, anomalously, it's like changing where you heat the flame is under a pot of boiling water. You now introduce a new heat source in this huge surface area of the Earth, and as a result this has knock-on effects to the mean atmospheric circulation in response to heating anomalies by the surface of the Earth. So, in addition to its global influence, a second reason for all the fuss about ENSO is that we have also managed to obtain some skill in predicting ENSO events several months in advance. Some of you may have seen several articles this year noting that scientists are predicting an El Niño event at the end of the year. We are able to get several months of predictability because of the ocean's role within ENSO. The ocean is the slow part of the system, and when we see subsurface heat content anomalies propagating from the western part of the Pacific to the eastern part of the Pacific, this suggests that an ENSO event could form. So the first fact about the ocean that we need to appreciate to understand why we actually have the El Niño Southern Oscillation in the first place is that we have to appreciate that the ocean is on average incredibly cold. So as you see with this figure here, it's only a very thin layer of water in the surface of the tropical Pacific Ocean that is actually warmer than 12 degrees centigrade. And the fact that we have this very thin layer of warm surface water on what in general is sort of water near 3 degrees Celsius, quite cold water, means that in the mean state, when we look at the mean state of the Pacific Basin, so here we're looking along the equator, and this is North America, South America, and here you have Australia. So this is the Western Pacific, and we see this warm pool, warm temperatures where we have convection. And what's surprising is actually here in the Eastern Pacific, you're right on the equator, so you're getting the most solar radiation, heating sea surface temperatures. But you actually have surprisingly cold, sort of 23 degrees Celsius water sitting here right on the equator. And this is referred to as the Eastern Equatorial Pacific Cold Tongue. And it's supported by the fact that you have easterly winds as part of the Walker circulation. So you have air rising over the warmest waters and subducting over the colder water in the east. And that's causing winds because the Coriolis effect is zero at the equator. We actually have the winds going directly from the high pressure to the low pressure. And this is piling up all the water in the western part of the basin, and it's shoaling the thermocline, which is separating that I showed you in the previous slide, a very thin layer of warm water from the rest of the deep cold water. And so you actually have the warm water piling up in the western part of the basin and exposing the cold water that's down below at the surface. And this is essentially a coupled process because you need the winds to pile the water up in the west, but you need the sea surface temperature gradient to drive the winds in the first place. And so this is inherently a coupled ocean atmosphere process. Now, what happens when you have an El Niño event is you actually have a relaxation of these winds, El Nino conditions or an El Nino event occurs when we have a deviation from normal conditions, and that, for example, if we had a westerly wind burst, so typically the winds here are easterly, and if we have weaker than normal easterlies here, this allows the thermocline slope to relax a little bit, and some waves, which are referred to as Kelvin waves, to propagate from the west to the east, as a result warming the sea surface temperatures in the east. And when they start to warm in the east, this is actually reinforces the whole process, because what happens is the east-west SST gradient decreases, and so the winds start to relax even further, which then allows even more heat to travel from the west to the east, and the thermocline to relax its slope even further. And this coupled feedback is called the Birkenes feedback, where winds relax, sea surface temperature, east-west gradient relaxes, thermocline slope relaxes. This helps the winds to relax even further, and this results in the growth of an El Nino event. The opposite is true for La Nina conditions. So as opposed to the winds relaxing, we actually have the winds increase in magnitude, which causes increased cooling in the east and increases the slope of the thermocline, and then helps to reinforce the strength of the Walker circulation. And so the El Nino-La Nina Southern Oscillation is essentially the oceanic conditions in the Pacific, equatorial Pacific, oscillating between these states of La Nina-like conditions and El Nino-like conditions. And the timescale of these oscillations are set by the timescale of oceanic adjustment. Because at some point, once you've formed an El Nino event or La Nina event, oceanic adjustment, and I won't go into all the details for the point of this lecture, but oceanic adjustment actually results in the reversal, so a delayed negative damping effect, which brings the events to an end. So it brings an El Nino event or La Nina event to the end by changing the sign and causing the oscillation to return to, well, the perturbation to return to normal conditions. So let's just quickly show you a few cool animations of the sort of sea surface temperature variability in the oceanic adjustment. So this animation here is particularly cool. What we're looking at is a slice along the equator in the Pacific Basin. That's the west, and this is the east here, closest to us. And so here you see the thermocline slope. The thermocline is deepest in the west and shoaling in the east. And this is because the winds are blowing from the east to west. Here we're going through 2010, when we had a La Nina, then 2011, which is normal conditions. Towards the end of 2011, we had La Nina again, and then we're going to 2013 as normal conditions, and then 2014 we see like it's looking as if it's going towards El Nino-like conditions. So when it's an El Nino-like state, we have a weak gradient and warm SSTs, and here you can also see the sea surface temperature, sea surface height perturbations. So there's divergence in the currents causes depression in sea surface height and cooling of sea surface temperatures as the thermocline wells. So this is a great graphic. This is another one looking along the equator, and I'm just going to have to try and refresh my screen so you can see this. So what we're seeing here is a west-east view along the equator. Here we see the thermocline shoaling from the west to east. Here we see the winds blowing on the surface, and we see the winds accelerating as SSTs get cooler here, and you have a La Nina event. And then we see them decelerating when you have an El Nino event, and the sea surface temperatures get warmer. This is just showing how the oceanic adjustment is playing a role in the development of colder than normal or warmer than normal sea surface temperatures in the eastern part of the basin. Here's looking at 2014. This is a website showing sea surface temperature from August, September, so July, August, September sea surface temperatures. And here we see the anomalies. And so what we can see is that there was a a warmer than normal eastern Pacific sea surface temperature anomaly developing. And so this is leading researchers to think that we will have El Nino conditions peaking in November, December this year. Originally, we were forecasting quite a big one, but now the dynamics have changed slightly, and the forecast is for more of a moderate El Nino. Okay, so that pretty much sums up what I wanted to illustrate to you about the El Nino Southern Oscillation. And just to end off this talk about oceanic circulation and sort of the review of the great talk that Haley gave, I'd just like to leave you with a bit of a thought experiment. So as Haley explained how Earth's rotation by the Coriolis effect deflects oceanic motions to the left in the southern hemisphere and to the right in the northern hemisphere, how do you think the large-scale wind patterns and ocean gyres would change if the Earth rotated the other way? Okay, so that's just a bit of food for thought. And that's all from me for this critique of Haley's talk on oceanic circulation. Thanks.